the topic today is extrema and an interval. This corresponds to section 4.5 in our textbook. In this unit, we're going to look at function analysis. So given a graph or given an equation, the visual or the analytic, what can you say about the function? What is the intervals of increasing, decreasing, where are maximums and minimums, really turning you into a walking, talking, graphing calculator, okay? So this unit, this chapter, really should make you much more able to work with functions and to talk about properties of functions by hand without any technology. So, extrema of a function, you kind of are looking at these questions. So, where does a maximum or minimum value occur? When is the function increasing? When is it decreasing? Alright? And depending on what you're given to work with, your answers vary, okay? So, for figure 1, it's a closed interval, so from -1 to 2 for the x values, so we could use brackets to say closed the inclusive interval, so included from -1 to 2. And if you want to see that as inequalities, that's the same as -1 less than or equal to x, less than or equal to 2. So on this closed interval, you see a minimum right here, the lowest point. And because it is the lowest point on the graph, not a low point, the lowest, we could call that, my writing kinda sloppy, let me try that again. I'll just use this, zoom in a little more. So, that is an absolute. Oh boy, that does. Alright, absolute minimum. Also, an absolute maximum is the highest point, not a high point. Example 2, we have two open circles at the end of each of the interval at each end. So this is parentheses, -1 to 2. So that's the exclusive interval, or the open. You're excluding, not including, the endpoints. And now I want to use this more, so I'll go back to it. Ready to go. So, if you want to see interval or inequalities for this, this is the same as -1 less than x less than 2. For example 3, we see open circle at the bottom, we see closed circles at the endpoints. So this would be the interval closed from -1 to open 0, and then open 0 to 2 closed. And we see in example 3, there is no minimum, because the lowest point is an open circle. And you could say, well, hey, isn't this the lowest point? Well, load out one just to the right of it, but not on the open circle. It's like the one-up game. You can constantly one-up another person. It's like a younger sibling, always saying they can do one more, one better, just to get under your skin. So with that open circle, you can get infinitely close to it or infinitely closer to it. But because you can always do that, you can say you can say like you want to get closer to 1, okay? So you can say, well, 0.9 or 0.99 or 0.999 or 0.9999. You can always get closer. So no minimum because there's an open circle. There's a maximum because there's a highest point. Here, no minimum. There's a minimum because that bottom of the curve is continuous. It goes all the way through smoothly. But then up here, of course, no maximum because you can always get closer and closer and closer to the point or to the open circle. All of this leads us to the extreme value theorem. So there's a hypothesis, there's an if-then, you have to fulfill the hypothesis, okay? So for the extreme value theorem, f has to be continuous on a closed interval. That's important. A closed interval, inclusive a to b. If that's the case, f has both a maximum and a minimum. And I'm going to kind of edit that a little. I'm going to say both are absolute maximums and minimums, okay? Relative extrema, relative maximums occur at a low point, not the lowest point, or a high point, not the highest point. So you can see this graph goes down to the left, so it keeps going, goes up to the right, it keeps going, okay? So that means to the right, the graph is going to keep going up. It's going to be higher than this point right here. So that point is not the highest point, it is a high point. You can think of it as like a high point in the neighborhood. It's the highest point in a region, a subset. So around it is the highest point of points around it. Relative minimum right there. It is a low point on the graph. It's the lowest point in that neighborhood, that region, okay? So absolutes, relatives, they're different. Absolutes happen when you have a closed interval. Relatives can happen really any time, okay? So moving on to the next page. Again, lot of definitions to start this unit. We gotta kind of get all of our vocabulary on the same page so we know what each other's talking about, okay? When I say things, I'm gonna use specific language to help you kind of narrow down what is true. Then when you say things, you want to use that specific language so that I know what you are talking about and what you mean to say. So relative extrema are extreme values, so minimums and maximums. You look at them primarily on open intervals, okay? So you're looking at an open interval of containing C. F of C on that open interval is a maximum. It's a relative maximum. So you're looking at a whole graph, just zeroing in on that part of the graph. Alright? There's relative minimums also, okay? Now, critical numbers. This is so critical. Bad joke. Sorry, not sorry. Okay. Critical numbers. It's important that at the very get-go, let f be defined at c. So the function exists. Which might seem like a throwaway statement, but it's kind of important. Like, if there's going to be a critical number, the critical number has to be there in the first place. The function has to exist for the critical number to fall in it. If there's nothing for the critical number to fall on, it goes away, okay? So your function has to exist at c. If the derivative at c equals 0, or f is not differentiable, so critical number, or the derivative is 0, or not differentiable, one of those two, then c is a critical number, alright? And if it's a critical number, it could be a relative extrema. Okay, could be. Relative extrema only occur at critical numbers. Not every critical number is a relative extrema, but every relative extrema is a critical number. Kind of like not every rectangle is a square, but every square is a rectangle, because every square has 4 right angles. Definition of rectangle is 4 right angles. So finding extrema on a closed interval, here's kind of some steps you can look at to kind of visualize and have a checklist of what you're going to do. But let's look at an example, okay? Find the absolute extrema of f of x on the interval -1 to 2. Oh wait, I forgot something. I want to write this down. So, just looked at my notes. I'm like, hey, don't forget that. So here we go. Number 1, find the critical numbers. Still up here. Okay. So finding the critical numbers. It's a really sloppy arrow. That means f prime of c equals 0, or f prime of c equals undefined, or d&e does not exist. And then right here, this can be pretty easily forgotten about when you're finding absolutes. You then need to evaluate f at each endpoint, okay? Because critical numbers could occur inside the interval, but then the endpoints could be higher or lower, kind of like that example 1 we saw, or figure 1. Critical number happens right here, but your endpoints are higher, okay? So you want to test the endpoint also to find any absolute extrema. Yeah, the critical number, the critical point there is an absolute minimum, but the maximum is an endpoint. So on the interval -1 to 2, so let's start finding critical points, critical numbers. Critical numbers and critical points, just to tell you, I'll kind of use those interchangeably, okay? So finding the derivative, this derivative of cubic well-behaved, so well-behaved functions won't have discontinuity, so this has the derivative at all points. All we gotta worry about is setting it equal to 0. Right, do a little algebra. Do a greatest common factor first. So pull out the 12x squared. We're left with x minus 1. And now some ZPP, zero product property. So that means 12x squared equals 0. Just do the simple algebra there. X is 0. Or x minus 1 equals 0. So do the algebra there. get 1. So those are our critical numbers. So we then want to test those critical numbers, and you want to test the endpoints also. So for writing absolutes with a closed interval, you want to test critical numbers and the endpoints. So -1, I don't like that. -1, 0, 1, and the other endpoint, 2. Plug those into f(x), get 7, 0, -1, and 16. So we have our critical numbers here and here, 0 and 1. And then because we're finding absolutes, testing our endpoints also. Up there and down here. So remember, with the closed interval, you're finding absolutes. Don't forget, closed interval. You want to test your endpoints also. So when you see that closed interval, don't forget, test your endpoints. If you're only finding relatives or it's an open interval, you don't have to. When it's closed, make sure you do that. So kind of graphing this, we see -1, 7, so -1, 7, kind of this is a pretty sloppy graph, but it'll work. We have 0, 0, we have 1, -1, we have 2, 16. So you kind of see it go down, level out, go down again, and up. Again, sloppy graph, okay? So we have our critical numbers right there. And you can see from the graph and from our table of values, we have an absolute maximum or minimum. I'm going to say max, but write min, so we'll go with that. At x equals 1, which is the ordered pair, kind of going back to the table, 1, -1. We have our absolute max at 2, x equals 2. That ordered pair is 2, 16. So I'm kind of given the kind of every answer I could give. Where does it occur at the x value, and what is the ordered pair? I hope you're in class. So where it occurs, what the ordered pair is. I've left out one thing. If they say what is the absolute minimum or what is the absolute maximum value, you give the y. The absolute minimum value is y equals -1. The absolute maximum value is y equals 16. Okay? This question says find the absolute extrema, so I give the x value where it occurs and the ordered pairs. They don't say find the absolute extrema values. Okay? Examples B and C, look at those and check my notes online. I kind of want to talk about this one and then let you try it on your own, okay? Finding the minimum slope. Find the smallest possible slope. So think about it. You're finding the smallest. Gonna highlight. Find the smallest slope. So you're minimizing a slope. Can be. Gotta think when I say slope. What should you think? What should be in mind synonymous with slope? Okay, that should be your derivative. So you're finding a minimum derivative, so a minimum of the derivative. We've been finding extrema of a function, so you work with the function and the function's derivative. Now you're finding a minimum of a derivative. So you're going to work with the derivative and the second derivative, okay? So let's kind of write this out. We've been finding max or min values. Alright, max or min values. That means you work with f of x and f prime x. F prime x, find when it equals 0 or equals undefined. Those are your critical numbers. You plug that into f of x along with endpoints. Alright, so that's kind of summing up what we've been doing. Finding maximum values. Work with f and f prime. Your critical numbers, then you plug into fx along with endpoints. Now this problem here, finding a smallest possible slope, so a minimum slope value. Slope synonymous with the derivative. You're going to find a minimum derivative value. So what should you do here? Okay? Gonna take all this, gonna copy it. All of the same stuff, okay? But now I'm gonna change just a few things. Instead of values, gonna have slopes. Alright, that's my first difference. Values, now slopes. So instead of change values to slopes, f of x changed to f prime changed to f double prime. I introduced a derivative here. So now introduce a derivative here and here. And then over here, f of x, introduce a derivative, so into f prime. So I'll talk more and more about a ladder. And a function, derivatives, second derivatives, thirds, fourths, are rungs on a ladder. So your function, down a rung derivative, down a rung second, down a rung third. So minimum, maximum values are in the first two rungs, fx, f prime. Min, max slopes move down a rung, f prime, f double prime. Alright, take a look at all the examples in the notes. Check your work with my completed notes online.